In this video, the aim is to explore how gravity works around the universe, not as a single uniform rule, but as something that takes on different expressions in different environments. From planets and moons to stars, galaxies, and the space between them, this is a slow and steady journey through how gravity shapes the universe. There is no rush and no need to hold everything at once, just a calm exploration of a force that feels simple close to home and grows quietly more complex the farther out you go. Gravity is usually encountered long before it is ever named. It is present in the way feet meet the ground, in the way objects fall when released, and in the quiet certainty that things tend to stay where they are unless acted upon. There is no obvious sensation announcing its presence, no vibration, no sound, no visible signal. Instead, gravity feels like the default condition of existence, so reliable that it fades into the background of awareness. On Earth, gravity gives weight to the body. It presses gently downward at every moment, providing resistance that muscles learn to work against from the earlier stages of movement. Standing, walking, sitting, lifting, and even resting are all shaped by this steady pull. Because it never switches off, it rarely attracts attention. Like air pressure or the passage of time, gravity becomes noticeable mostly in its absence or when something goes wrong. When an object is dropped, it falls. When a glass slips from a hand, it accelerates downward and breaks on the floor. These events feel obvious and unsurprising, as if they could not happen any other way. Over time, the mind stops questioning them. Gravity becomes not just familiar but expected. It appears uniform, predictable, and unchanging. This sense of constancy is reinforced by everyday experience. Whether indoors or outdoors, whether near sea level or on a modest hill, gravity feels the same. A cup weighs the same in the kitchen as it does in the garden. The body feels no lighter or heavier from one moment to the next. From a human perspective, gravity seems fixed, almost absolute. Yet even on Earth, gravity is not perfectly uniform. Its strength varies slightly depending on location. The pull of gravity is marginally weaker at the equator than at the poles, due to the planet's rotation and its slightly flattened shape. Altitude also plays a role. Gravity is fractionally weaker on a mountain than at sea level, because distance from Earth's center increases. These differences are small, far below the threshold of human sensation, but they are measurable with sensitive instruments. The reason gravity feels so constant is not because it truly is, but because human perception is limited. The variations that exist are subtle enough to be smoothed out by the scale of everyday life. Muscles, bones, and balance systems adapt to the local gravitational environment and treat it as normal. Over time, that normal becomes invisible. Historically, gravity was first understood not as an invisible background condition, but as a force acting between objects. In the late 17th century, Isaac Newton described gravity as a universal attraction between masses. According to this view, every object with mass pulls on every other object with mass. The strength of that pull increases with mass and decreases with distance. This idea provided a powerful explanation for falling objects, planetary motion, and the orbits of moons. Newton's description of gravity was revolutionary because it unified events on Earth with motion in the sky. The same force that causes an apple to fall also keeps the moon in orbit around Earth and governs the paths of planets around the sun. Gravity was no longer just a local phenomenon. It was universal, operating everywhere in the cosmos. For centuries, Newtonian gravity provided accurate predictions for most situations encountered in daily life and astronomy. It explained why objects accelerate downward at a roughly constant rate near Earth's surface. It described why planets follow stable, repeating paths. For practical purposes, it worked extremely well, and it still does in many contexts. However, Newton's gravity also reinforced the idea that gravity behaves the same everywhere. While the equations allowed for variation in strength, the underlying picture suggested a single, consistent rule applied uniformly across space. This reinforced the everyday intuition that gravity is a fixed property of the universe, rather than something that can take on different forms. In reality, the experience of gravity on Earth represents only one local expression of a deeper phenomenon. Earth is a medium-sized rocky planet with a specific mass, radius, and internal structure. Its gravity is strong enough to hold an atmosphere, shape oceans, and anchor life to the surface, but not so strong as to crush structures or prevent movement. This balance feels natural only because life evolved within it. If Earth were slightly more massive, gravity would be stronger. Objects would weigh more, movements would require greater effort, and biological structures might need to be more robust. If Earth were less massive, gravity would be weaker. Objects would fall more slowly, jumps would carry higher arcs, and the atmosphere might be thinner or escape into space. Small changes in planetary mass lead to noticeable changes in gravitational experience. Because Earth provides a stable and narrow range of conditions, it is easy to mistake that local balance for a universal standard. Gravity feels like a constant because it has been constant within the limits of lived experience. But those limits are small when compared to the range of environments found across the universe. Even within the solar system, gravity varies dramatically. The Moon's gravity is much weaker than Earth's, allowing astronauts to lift themselves with ease and objects to fall slowly in graceful arcs. Jupiter's gravity is far stronger, enough to compress matter to extreme densities and dominate the motion of nearby objects. These differences do not require new laws of physics. They emerge naturally from differences in mass and size. The key point is that gravity is not something that simply exists at one strength everywhere. It depends on the properties of the objects involved. Mass, distance, and distribution all matter. The gravity felt on Earth is the result of Earth's particular combination of these factors, not a default setting of the universe. Understanding gravity as a local experience rather than a universal constant opens the door to a broader view. It invites curiosity about how gravity behaves in other places, under other conditions, and at other scales. The familiar downward pull becomes one example among many, rather than the defining case. By starting from what feels obvious and dependable, it becomes possible to gently question those assumptions. Gravity does not change abruptly from place to place, but it does change meaningfully. The version experienced on Earth is not wrong or incomplete, but it is specific. It belongs to this planet at this distance from its center, with this mass beneath the surface. Recognizing that fact does not make gravity less reliable. Instead, it places it in context. Gravity remains one of the most consistent features of the universe, but consistency does not mean uniformity. What feels constant here is part of a much wider pattern, one that stretches far beyond the ground beneath your feet. Gravity is often spoken about as a force, something that pulls objects together across empty space. This description works well enough for many everyday situations, but it is not how gravity is understood at the deepest level. In modern physics, gravity is not treated as a mechanical pull or an invisible tether stretching between objects. Instead, it is understood as a fundamental interaction that emerges from the structure of the universe itself. To see why this distinction matters, it helps to notice how gravity differs from other forces that feel more familiar. When a hand pushes a door, there is contact. When a magnet attracts metal, there is a visible interaction that weakens quickly with distance. Gravity behaves differently. It acts between objects regardless of what lies between them. It cannot be blocked, shielded, or turned off. Its influence extends across vast distances, shaping the motion of planets, stars, and galaxies alike. For a long time, gravity was described using the framework developed by Isaac Newton. In that picture, gravity is a force of attraction between masses. The larger the masses, the stronger the attraction. The farther apart they are, the weaker the pull. This description is simple, intuitive, and remarkably effective. It explains falling objects, planetary orbits, and the predictable motion of moons and comets. Even today, it remains accurate enough for many practical purposes, from engineering to spaceflight planning. However, Newtonian gravity leaves an important question unanswered. It describes how gravity behaves, but not what gravity actually is. It treats gravity as a force acting instantaneously across space, without explaining the mechanism by which that influence travels. As scientific understanding advanced, this limitation became increasingly difficult to ignore. In the early 20th century, Albert Einstein offered a radically different way of thinking about gravity. Rather than treating it as a force acting across space, Einstein described gravity as a consequence of the geometry of spacetime itself. This idea forms the foundation of general relativity, published in 1915, and it remains the most accurate description of gravity currently available. In this view, space and time are not separate backgrounds against which events unfold. They're combined into a single physical structure called spacetime. Spacetime has measurable properties. It can be stretched, compressed, and curved. Mass and energy tell spacetime how to curve, and that curvature tells matter how to move. Under general relativity, objects do not fall because they are pulled by a force. They fall because they are following the straightest possible paths through curved space-time. These paths are called geodesics. To an observer embedded within space-time, this motion appears as acceleration. From the inside, it feels exactly like a force acting downward. This idea can feel abstract at first because curved space-time is not something that can be directly seen or touched, but its effects are measurable and precise. One of the key insights of general relativity is that gravity affects not only motion, but also time itself. Clocks tick at different rates depending on their position in a gravitational field. Time runs slightly slower, closer to massive objects, and slightly faster farther away. This effect has been measured repeatedly using atomic clocks, and must be accounted for in satellite navigation systems to maintain accuracy. The difference between Newtonian gravity and relativistic gravity is not that one is wrong and the other is right. Newton's description is an approximation that works well when gravitational fields are weak and speeds are much slower than the speed of light. General relativity becomes essential when gravity is strong, distances are large, or extreme precision is required. On Earth, the difference between these descriptions is subtle. Everyday experience does not reveal the curvature of space-time. Objects still fall downward, orbits remain stable. The familiar picture of gravity as a force continues to work. This is why gravity feels simple and intuitive at human scales. The deeper structure is hidden beneath effects that are too small to notice directly. Space-time itself is not a passive stage. It responds dynamically to the presence of mass and energy. A massive object like Earth curves the space-time around it. Objects moving nearby naturally follow paths shaped by that curvature. The Moon follows a curved path around Earth, not because it is being tugged sideways, but because it is moving through a curved space-time geometry created by Earth's mass. An important feature of this picture is that gravity is not something added on top of space. It is built into the shape of space and time themselves. Where space-time is more curved, gravity appears stronger. Where space-time is flatter, gravity appears weaker. This provides a natural explanation for why gravity varies from place to place, without requiring any change in physical laws. This also explains why gravity behaves differently from other forces. There is no gravitational substance flowing between objects. There are no particles carrying gravity in the everyday sense. Instead, there is a continuous geometric structure that governs motion everywhere. Objects respond to that structure simply by existing within it. One way to understand this intuitively is to imagine motion without gravity. In empty, flat space-time, an object moves in a straight line at constant speed. This is the natural state of motion. Gravity changes what counts as a straight line by altering the geometry through which objects move. What appears curved or accelerated to an observer is actually straight motion within a curved space-time. This perspective also clarifies why gravity cannot be switched off. As long as mass and energy exist, space-time will have structure. As long as space-time has structure, motion will be guided by that structure. Gravity is not a feature layered onto the universe, it is woven into its geometry. Importantly, general relativity predicts effects that Newtonian gravity cannot. These include the bending of light around massive objects, known as gravitational lensing, and the precise precession of planetary orbits. These predictions have been confirmed through observation and experiment, reinforcing the idea that gravity is best understood as geometry rather than force. Despite its conceptual depth, this view of gravity does not contradict everyday experience. It explains why gravity feels steady and uniform on Earth, while allowing for dramatic variation elsewhere. Near extremely massive or dense objects, space-time curvature becomes intense, leading to effects that have no Newtonian equivalent. In regions with very little mass, space-time becomes nearly flat, and gravity grows faint. By moving from a force-based picture to a geometric one, gravity becomes something both simpler and more profound. Simpler because it requires no mysterious action at a distance. More profound because it ties together space, time, motion, and mass into a single framework. This shift in understanding replaces an intuitive but incomplete idea with a deeper model that still accounts for everything already known. The sensation of weight, the fall of objects, and the motion of planets all remain exactly as experienced. What changes is the explanation beneath those experiences. Gravity in this view is not something acting within the universe, it is part of what the universe is. Gravity varies because the universe is not uniform. Objects differ in mass, they occupy different positions, and they are separated by different distances. These differences matter. They shape how strongly gravity acts and how that influence is felt from one place to another. What feels steady and unchanging on Earth is the result of very specific conditions that are not repeated everywhere. In its simplest description, gravity depends on two main factors: how much mass is involved and how far apart objects are. More mass produces a stronger gravitational influence. Greater distance weakens that influence. This idea appears clearly in Newtonian gravity, where the strength of gravity increases with mass and decreases rapidly as distance grows. While the deeper explanation of gravity comes from curved space-time, this relationship between mass, distance, and strength remains valid and observable. On Earth, distance from the planet's center changes very little during everyday movement. Standing up, sitting down, or walking across a room alters that distance by only a tiny fraction. Because the mass of Earth is large and the variation in distance is small, gravity feels constant. The changes are too subtle to notice without instruments designed specifically to detect them. As distance increases, however, gravity weakens. This weakening does not happen abruptly. Gravity does not switch off beyond a certain point. Instead, it fades gradually, becoming less influential the farther away an object moves. The pull never fully disappears, but it becomes increasingly difficult to detect as distance grows. The Moon provides a useful example. Earth's gravity is strong enough to keep the Moon in orbit, even though the Moon is hundreds of thousands of kilometers away. At that distance, Earth's gravitational influence is weaker than it is at the surface, but it is still strong enough to guide the Moon's motion. The Moon, in turn, exerts its own gravitational influence on Earth, producing tides in the oceans. This mutual interaction shows that gravity extends far beyond the surfaces of objects and operates across empty space. Move farther still, and Earth's gravitational influence continues to weaken. At the distance of the Sun, Earth's gravity is negligible compared to the Sun's. The Sun's mass is so much greater that it dominates the motion of planets, asteroids, and comets throughout the solar system. Earth becomes just one contributor among many, its gravitational role reduced by distance and by comparison with a far more massive object. This pattern repeats throughout the universe. Small bodies like asteroids exert only weak gravitational influence. Planets exert more. Stars exert much more. Entire galaxies containing billions of stars produce gravitational effects that shape vast regions of space. At each step, mass and distance work together to determine how gravity behaves. It is important to understand that gravity weakens smoothly rather than fading in steps. There is no boundary where gravity suddenly ends. Even objects separated by immense distances still exert some gravitational influence on one another. The effect may be so small that it has no practical consequence, but it is never truly zero. This gradual fading is one reason gravity can be difficult to conceptualize. Human intuition often expects forces to have clear limits. Pushes and pulls usually stop when contact ends. Gravity does not behave that way. Its influence stretches outward indefinitely, thinning with distance but never vanishing completely. To describe this extended influence, physicists use the concept of a gravitational field. Gravitational field is not a physical substance filling space. It is a way of describing how gravity acts throughout a region. At every point in space, the gravitational field has a certain strength and direction, determined by the mass and distribution of nearby objects. Thinking in terms of gravitational fields helps clarify why gravity varies. Near a massive object, the gravitational field is strong. Far away, it is weak. Where multiple masses are present, their fields overlap and combine, creating complex patterns of influence. The gravity experienced at any location is the result of all relevant fields acting together. On Earth's surface, the gravitational field is dominated by Earth's mass. Contributions from the Moon, the Sun, and distant planets are present but small. They add subtle variations detectable with sensitive measurements but not noticeable in daily life. This dominance creates the impression that gravity is simple and singular. As environments change, so does the balance of gravitational fields. On the Moon, Earth's gravitational field competes with the Moon's own weaker field. In deep space, far from large bodies, gravitational fields become faint and diffuse. Motion there is governed by whichever mass exerts the greatest influence, even if that influence is small. From a relativistic perspective, this variation reflects changes in space-time curvature. Mass and energy curve space-time, and that curvature becomes gentler with distance. Close to a massive object, space-time is more strongly curved, guiding motion sharply. Far away, space-time flattens, and paths straighten out. The transition is smooth, continuous, and predictable. This explains why gravity cannot be uniform across the universe. The universe contains objects of vastly different masses, arranged in complex patterns. There is no single gravitational environment that applies everywhere. Each location has its own balance of influences, shaped by nearby matter and energy. Even within a single planetary system, gravity varies dramatically. The surface of a rocky planet, the upper atmosphere of a gas giant, and the space between planets all present different gravitational conditions. These differences affect how matter behaves, how objects move, and how structures form over time. One quiet implication of this is that gravity is always local. It is shaped by what is nearby, and by how far away those influences are. The gravity experienced at any point is not a universal constant imposed from outside. It is the result of the surrounding universe acting through mass, distance, and geometry. This locality helps explain why gravity feels so dependable, while also being so variable. In any given place, the gravitational environment changes slowly. Large masses move on long timescales. Distances shift gradually. As a result, gravity appears stable within a local frame of reference, even though it differs widely from one region to another. Understanding gravity as something that varies with mass and distance provides a bridge between familiar experience and the wider universe. It shows that the steady pull felt on Earth is not an exception or a rule, but one outcome among many. The same principles apply everywhere, but their effects depend on where and what you are. Gravity does not behave differently because the laws change. It behaves differently because the universe is not the same everywhere. Within a single solar system, gravity already shows a remarkable range of behavior. The same physical principles apply everywhere, but the experience of gravity changes from world to world in ways that are immediate and tangible. By comparing a few familiar destinations, it becomes clear that gravity is shaped not just by size, but by deeper properties such as density, composition, and internal structure. On Earth, surface gravity provides the baseline for nearly all human intuition. Objects fall at a steady pace. Bodies have weight that feels neither crushing nor negligible. The planet's mass and radius combine to produce a surface gravity that life has adapted to over billions of years. Muscles, bones, circulation, and balance systems are all tuned to this particular gravitational environment, making it feel natural and unremarkable. The Moon offers the first clear contrast. With far less mass than Earth and a smaller radius, its surface gravity is much weaker. An object that weighs 100 kilograms on Earth would weigh roughly 16 kilograms on the Moon. Astronauts visiting the lunar surface experienced this difference immediately. Movements became slow and floating. Simple steps turned into bounding arcs. Objects dropped from hand height took noticeably longer to reach the ground. This reduced gravity does not come from the Moon being small alone. It also reflects its internal structure. The Moon is less dense than Earth, with a smaller metallic core and a simpler geological history. Less mass packed into a smaller volume produces a weaker gravitational field at the surface. The result is a world where gravity is gentle enough to reshape motion without eliminating it entirely. Mars provides a different variation. Larger than the Moon but smaller than Earth, Mars has a surface gravity that sits between the two. A person standing on Mars would weigh a little over 1/3 of their Earth weight. This difference is large enough to affect movement and long-term health, but not so extreme as to make walking unfamiliar. Mars also illustrates how composition matters. Despite being larger than the Moon, Mars has lower density than Earth. Its core is smaller relative to its size, and its overall mass is lower than its diameter alone might suggest. As a result, surface gravity remains modest. Data gathered by NASA missions such as the Viking landers, the Mars exploration rovers, and the Curiosity and Perseverance rovers have helped refine measurements of Martian gravity and confirm how closely it matches theoretical predictions. Standing on Mars would feel lighter but still grounded. Objects would fall more slowly. Jumps would carry higher and longer. Over time, the body would adjust to the reduced load on bones and muscles. These changes are not hypothetical. Studies of astronauts aboard space stations combined with robotic mission data help scientists understand how gravity influences physiology and movement. The gas giants introduce a more counterintuitive case. Jupiter, the largest planet in the solar system, has a surface gravity stronger than Earth's, despite having no solid surface in the traditional sense. At the level of its cloud tops, gravity is more than twice as strong as Earth's. A person somehow supported there would feel significantly heavier, even though Jupiter is made mostly of hydrogen and helium. This stronger gravity comes from Jupiter's immense mass. Although its density is lower than Earth's, its sheer size means that enormous amounts of material are packed into a vast volume. The result is a powerful gravitational field extending far into space. Jupiter's gravity dominates the solar system after the Sun, shaping the orbits of moons, asteroids, and even influencing comet paths. Saturn, despite being nearly as large as Jupiter, has lower surface gravity. Its density is much lower, meaning less mass is concentrated within its radius. This comparison highlights an important point. Size alone does not determine surface gravity. Density and mass distribution are equally important. A larger planet can exert weaker gravity if its material is spread more thinly. These planetary differences explain why standing on different worlds would feel radically different. On the Moon, the body would feel light and buoyant. On Mars, movement would feel easier, but still familiar. Near Jupiter's cloud tops, weight would increase dramatically, making even small motions more demanding. None of these experiences require changes to physical laws. They arise naturally from how mass is arranged. NASA's planetary missions have played a key role in confirming these differences. Tracking spacecraft trajectories, measuring orbital speeds, and analyzing lander data allow scientists to map gravitational fields with high precision. Missions such as Juno around Jupiter and Lunar Reconnaissance, Orbiter around the Moon, have revealed subtle variations caused by internal structures, mountain ranges, and hidden mass concentrations. These measurements show that gravity is not perfectly uniform even across a single planet. Variations in crust density, underground structures, and geological history all contribute to small local differences. On Earth, these differences are used to study tectonic activity and resource distribution. On other planets, they reveal information about formation and evolution. What emerges from these comparisons is a clear pattern. Surface gravity depends on the balance between mass and radius, shaped by composition and internal structure. Two planets of similar size can feel very different. Two planets with similar gravity can have very different appearances. Gravity is sensitive to what lies beneath the surface as much as to what is visible from space. These planetary examples bring abstract ideas into physical terms. Gravity is no longer just a concept tied to equations or space-time curvature. It becomes something that can be felt, measured, and compared. The solar system becomes a natural laboratory, where gravity reveals its variability without leaving home. By examining neighboring worlds, gravity stops being a single familiar sensation and becomes a spectrum of experiences. Each planet represents a different outcome of the same underlying principles. Together, they show that even within one star's reach, gravity has many expressions, each shaped by the history and makeup of the world beneath it. Stars appear calm from a distance. They rise and set, shine steadily, and seem unchanged across human lifetimes. Beneath that steady light, however, gravity is at work in a far more intense and complex way than it is on any solid world. Inside a star, gravity is not confined to a surface. It acts throughout the entire volume, shaping structure, motion, and long-term stability from the center outward. A star begins as a cloud of gas and dust drawn together by gravity. As material accumulates, gravitational attraction strengthens, pulling more matter inward. Over time, this inward pull becomes strong enough to compress the central regions of the forming star. Temperatures rise, densities increase, and nuclear fusion begins. At this point, gravity does not disappear. Instead, it becomes part of a delicate balance. Inside an active star, gravity constantly pulls matter inward toward the core. At the same time, energy released by nuclear fusion produces heat and pressure that push outward. The state in which these opposing effects balance is known as hydrostatic equilibrium. It is this balance that allows stars to shine steadily for millions or billions of years, without collapsing or tearing themselves apart. Hydrostatic equilibrium is not static or fragile. It is a dynamic balance maintained moment by moment. If the core contracts slightly, temperatures rise, fusion rates increase, and outward pressure strengthens, restoring balance. If the core expands, temperatures fall, fusion slows, and gravity gains the upper hand again. This self-regulating process keeps stars stable across immense timescales. The strength of gravity inside a star depends strongly on stellar mass. More massive stars have stronger gravity throughout their interiors. This increased gravitational pressure raises core temperatures and accelerates nuclear fusion. As a result, massive stars burn through their fuel much faster than smaller ones. They shine brighter, live shorter lives, and experience more extreme internal conditions. In smaller stars, including the Sun, gravity is strong enough to sustain fusion but not so strong as to drive it rapidly. The Sun's mass produces core temperatures of roughly 15 million degrees Celsius, sufficient to fuse hydrogen into helium at a steady pace. This balance allows the Sun to remain stable for billions of years, providing a long window for life to develop on nearby planets. Gravity inside stars also determines how energy moves outward. In some regions, energy travels through radiation, with photons scattering repeatedly as they move toward the surface. In other regions, energy is transported by convection, with hot plasma rising and cooler material sinking. The structure of these layers is governed by the interplay between gravity, pressure, and temperature. Solar physics has provided detailed insight into this internal structure. Helioseismology, the study of oscillations on the Sun's surface, allows scientists to probe its interior indirectly. By measuring how waves travel through the Sun, researchers infer density, temperature, and motion deep beneath the visible surface. These measurements confirm theoretical models of how gravity shapes the Sun from within. Data from missions such as the Solar and Heliospheric Observatory and the Solar Dynamics Observatory have refined this picture further. Observations of solar vibrations, magnetic fields, and energy output all point to gravity as the organizing framework that holds the star together. Without gravity, nuclear fusion would disperse the star's material into space. Without fusion, gravity would cause the star to collapse. The balance between gravity and fusion is not permanent. As stars age and fuel supplies change, gravity gradually gains influence. When hydrogen in the core is depleted, fusion slows. Outward pressure weakens. Gravity responds by compressing the core further, raising temperatures until new fusion processes begin, if possible. This sequence drives stellar evolution and determines a star's ultimate fate. In very massive stars, gravity eventually overwhelms all opposing forces. When fusion can no longer provide sufficient pressure, the core collapses rapidly, leading to dramatic events such as supernova explosions. Even in these violent moments, gravity remains central, guiding collapse, rebound, and the formation of dense remnants. What is striking is that gravity inside stars does not merely pull material inward. It sets the conditions for energy production, regulates stability, and determines lifespan. It acts as an internal architect, shaping the star from the inside out rather than operating only at a surface boundary. This view expands gravity's role beyond what is experienced on solid worlds. On planets, gravity defines weight and structure. Inside stars, gravity governs balance, transformation, and long-term change. The same interaction that holds feet to the ground also sustains the steady light of stars across the galaxy. Understanding gravity inside stars highlights its versatility. It adapts to different forms of matter, from solid rock to hot plasma, while obeying the same underlying principles. This continuity is what allows gravity to operate across such a wide range of environments without contradiction. By recognizing gravity as an internal organizing force, the behavior of stars becomes less mysterious. Their stability, brightness, and evolution all follow naturally from the balance between inward pull and outward energy. Gravity does not simply act on stars, it defines what it means for a star to exist at all. Not all objects in the solar system are large enough for gravity to dominate their behavior in obvious ways. Beyond planets and large moons lies a population of small bodies where gravity operates at its weakest practical extreme. Asteroids, comets, and tiny moons occupy a regime where gravity is present but barely assertive, shaping environments that feel almost untethered. On these bodies, gravity is often described as microgravity. This does not mean gravity is absent, it means the gravitational acceleration at the surface is extremely small compared to that of Earth. On some asteroids, surface gravity can be tens of thousands of times weaker than Earth's. A gentle push could send an object drifting away at walking speed, never to return. This weak gravity arises from limited mass combined with small size. Many asteroids are only a few kilometers across, and some are far smaller. Even though they may be composed of rock or metal, there is simply not enough mass concentrated in one place to generate a strong gravitational field. The result is a world where weight is barely felt. Comets present a similar case, though with different composition. Often described as icy rubble piles, comets are mixtures of frozen gases, dust, and rock loosely held together. Their gravity is so weak that material can escape easily when heated by the sun. Jets of gas and dust stream outward, forming tails that stretch millions of kilometers through space. Gravity attempts to hold the comet together, but thermal forces frequently overpower it. Small moons orbiting planets also illustrate this regime. Some moons of Mars and the outer planets are irregularly shaped and lightly bound. Their gravity is strong enough to keep them intact under calm conditions, but not strong enough to reshape them into spheres. Many retain elongated or lumpy forms, reflecting their weak internal gravitational pull. In these environments, geology behaves very differently. On Earth, gravity drives landslides, erosion, and the settling of material into layers. On small bodies, loose material does not flow easily downhill because downhill is poorly defined. A slight disturbance can loft dust into space rather than causing it to settle. Surface features reflect this. Craters remain sharp and unchanged for long periods because erosion is minimal. Debris accumulates where it lands, not where gravity would normally draw it. Even walking on such a surface, if it were possible, would resemble slow-motion bouncing rather than stepping. Space missions have provided direct insight into these conditions. The Japanese Hayabusa mission visited the asteroid Itokawa and revealed a surface covered in loose gravel rather than solid bedrock. The asteroid appeared to be a rubble pile, a collection of fragments gently held together by gravity alone. This confirmed long-standing theories that many asteroids are not monolithic rocks, but loosely assembled structures. The European Space Agency's Rosetta mission offered a similar window into cometary gravity. By orbiting and eventually deploying a lander onto Comet 67P Churyumov-Gerasimenko, Rosetta demonstrated just how weak gravity can be. The lander bounced upon contact because gravity was insufficient to hold it firmly in place. Anchoring systems struggled because even small mechanical forces overwhelmed the comet's pull. These missions revealed an important truth. Weak gravity allows objects to exist in states that would be impossible on larger worlds. Loose material can remain exposed. Cavities can persist without collapsing. Internal structure can be fragile yet stable over long periods because external disturbances are rare. Gravity in these settings also reshapes internal structure. Without strong compression, material inside small bodies remains porous. Voids persist. Density varies irregularly. These characteristics influence how such objects respond to impacts, heating, and tidal forces from nearby planets. Even so, gravity still matters. It determines whether material escapes or returns. It governs orbital motion and long-term stability. It defines the boundary between what remains part of the body and what drifts away into space. The difference is one of degree, not of presence. Comparing these environments to planets highlights how scale transforms gravity's role. On planets, gravity dominates structure and motion. On small bodies, gravity is one influence among many, often competing with thermal forces, impacts, and rotational effects. This contrast reveals the lower limit of gravitational strength in the universe, as it is commonly experienced. There are environments where gravity is just strong enough to assemble material, but not strong enough to impose order. These worlds sit delicately balanced between cohesion and dispersal. Understanding gravity around small bodies completes the picture of variation within a single system. From crushing gravity inside stars to the barely perceptible pull of an asteroid, the same fundamental interaction operates across an enormous range of strengths. Gravity does not disappear as objects grow smaller. It simply becomes quieter, subtler, and easier to overlook. Orbit often feels unintuitive because it seems to contradict everyday experience. Objects that are dropped fall straight down. Objects that are thrown forward eventually land. From the surface of Earth, motion and falling appear to be separate things. In space, they are deeply connected. An orbit is not an object escaping gravity. It is an object falling continuously while never reaching the ground. This idea was described clearly by Isaac Newton through a simple thought experiment known as Newton's cannon. Imagine a cannon placed on a very high mountain, far above the atmosphere. A cannonball fired gently would fall to the ground not far from the mountain's base. Fired with more force, it would travel farther before landing. Increase the speed enough, and the cannonball would curve around the planet, falling toward Earth, but missing it entirely. In that case, the cannonball would be in orbit. The key insight is that gravity pulls the cannonball downward at all times. What changes is the forward motion. When forward speed is high enough, the surface of the planet curves away beneath the falling object. The object is always falling, but the ground is always falling away at the same rate. The result is a stable path around the planet. This reframes orbit as a balance between motion and gravity rather than a state of escape. Objects in orbit are not beyond Earth's gravitational reach. In low Earth orbit, gravity is only slightly weaker than it is at the surface. The International Space Station experiences nearly 90% of Earth's surface gravity, yet everything aboard appears weightless. This apparent contradiction leads to one of the most common misconceptions in space science: the idea of zero gravity. Astronauts are often described as floating because gravity is absent. In reality, gravity is very much present. What is absent is a supporting force. Weight is not the same as gravity. Weight arises when gravity is resisted by a surface. Standing on Earth, the ground pushes upward in response to gravity pulling downward. This interaction creates the sensation of weight. In orbit, there is no surface providing that upward push. Astronauts, spacecraft, and everything inside them are all falling together under gravity. Because everything is falling at the same rate, there is no relative motion between objects inside the spacecraft. Tools float, bodies drift, liquids form spheres. This condition is more accurately described as microgravity, or free fall, rather than zero gravity. The sensation of weightlessness comes from constant falling, not from the absence of gravity. This concept aligns closely with the modern understanding of gravity as geometry. In curved spacetime, objects move along natural paths, unless acted upon by other forces. An orbiting spacecraft follows such a path around Earth. Gravity guides motion rather than pulling objects inward like a rope. Seen this way, Orbit is not an active struggle against gravity. It is a passive response to it. The spacecraft does not need to continuously thrust to stay in orbit. Once placed on the correct path, it follows that path naturally, shaped by Earth's mass and the curvature of space-time around it. This perspective also explains why orbits can exist around many different objects. Moons orbit planets, planets orbit stars, stars orbit the centers of galaxies. In each case, gravity provides the curvature, and motion carries objects along stable paths through that curved environment. Distance plays a role in shaping these paths. Closer orbits require higher speeds to avoid falling inward. Farther orbits require less speed because gravity is weaker. These relationships can be calculated precisely, but the underlying idea remains simple. Orbital motion is continuous falling guided by gravity. The idea can feel counterintuitive because falling is usually associated with collision. On Earth, falling objects hit the ground quickly. In orbit, the scale is different. The curvature of the planet becomes part of the motion. Falling continues endlessly without impact as long as the path remains clear. Understanding orbit this way dissolves many common confusions. Satellites do not hover above Earth. They are not held up by outward forces. They're moving forward fast enough that their fall becomes a curve rather than a drop. This framing also helps explain why orbits can decay. Atmospheric drag, even very thin, slows objects slightly. Forward speed decreases. The balance shifts. The path curves more steeply inward, and the object eventually re-enters the atmosphere. Gravity remains constant throughout. What changes is motion. By viewing orbit as continuous falling, gravity becomes less mysterious and more subtle. It does not act as a simple downward pull that must be overcome. It shapes the pathways that objects naturally follow through space. Motion and gravity work together, producing stability without stillness. This understanding deepens the idea that gravity guides rather than restrains. It allows objects to move freely while remaining bound. What looks like suspension is actually perpetual descent, carefully matched to the curve of the world below. Empty space is often imagined as a place where gravity fades away, where distance dilutes influence until nothing meaningful remains. When stars disappear and galaxies recede into darkness, it can feel intuitive to assume that gravity must weaken to the point of absence. In reality, gravity does not vanish in empty space. It becomes quieter, more diffuse, and harder to notice, but it never fully leaves. What changes in regions far from stars and galaxies is not whether gravity exists, but how it is expressed. In dense environments, gravity is obvious. Objects fall, orbits tighten, and motion curves clearly. In sparse environments, gravity still operates, but its effects unfold slowly, stretched across immense distances and long spans of time. The absence of nearby matter does not remove gravity. It only reduces its immediate intensity. Gravity does not require visible objects nearby to function. Any object with mass contributes to the structure of space-time, and each contribution extends outward indefinitely. The influence weakens with distance, but it does not stop. A star affects space-time far beyond the reach of its light. A galaxy shapes motion well outside its luminous edge. Even when no obvious source is close, gravity reflects the combined influence of many distant masses. Interstellar space offers a useful example. Between stars, distances are vast, yet gravity remains active. Stars within a galaxy do not drift independently through emptiness. They orbit a shared center, guided by the collective gravitational field of billions of stars, clouds of gas, and unseen matter. At any point between stars, gravity is the result of overlapping influences. No single object dominates, but together they define how motion unfolds. Intergalactic space extends this idea further. Between galaxies, matter is extraordinarily sparse. Light can travel for millions of years without encountering a star. Even so, galaxies continue to move in structured ways. They drift toward clusters, trace long filaments, and avoid enormous regions known as cosmic voids. These patterns exist not because gravity is absent in empty space, but because gravity has already acted, pulling matter into denser regions and leaving behind quieter expanses. The idea of overlapping gravitational influence is central to understanding this behavior. Gravity does not come from one object acting alone. At every location in the universe, the gravitational environment reflects the sum of all relevant masses near and far. Nearby objects contribute strongly. Distant objects contribute weakly. Together, they form a continuous gravitational background rather than isolated zones of influence. This is why gravity cannot be escaped simply by traveling far from objects. Distance changes the balance of influences, but it does not remove them entirely. Even in the emptiest known regions of the universe, gravity still shapes how matter moves and how structures evolve. Large-scale cosmic surveys have revealed this structure with remarkable clarity. Observations from projects such as the Sloan Digital Sky Survey and the Dark Energy Survey map the distribution of galaxies across enormous volumes of space. These maps show that galaxies are not scattered randomly. They form a vast network often called the cosmic web, made up of filaments, clusters, and immense voids. This structure emerged over billions of years through gravitational interaction alone. Cosmic voids are sometimes mistaken for places where gravity does not exist. In fact, they are evidence of gravity at work. These regions are empty because gravity has pulled matter away from them. Small differences in density in the early universe were amplified over time as gravity drew material into denser regions. The voids themselves continue to evolve, expanding and reshaping under the same gravitational influence. From the perspective of general relativity, empty space is never truly empty. Spacetime exists everywhere, regardless of how much matter is present. Its geometry reflects the total mass and energy of the universe, including contributions from objects far beyond the local environment. In regions with little nearby matter, spacetime is closer to flat, but it is never completely free of curvature. This helps explain why motion through deep space remains predictable. Spacecraft traveling between planets are not drifting aimlessly. Their paths are guided by the combined gravity of the Sun, planets, and more distant bodies. Even when a spacecraft appears to be moving through emptiness, its trajectory reflects a carefully calculated gravitational landscape shaped by many sources. Gravity in empty space also plays a role in the long-term evolution of the universe. Over short timescales, weak gravitational influences seem insignificant. Over billions of years they accumulate. Small accelerations, barely noticeable in isolation, reshape structure across cosmic history. Galaxies drift together. Groups form clusters. Clusters assemble into even larger systems. None of this requires strong local gravity. It emerges from persistent, overlapping influence. Understanding gravity in empty space removes the idea that gravity must be tied to visible matter nearby. It is not something that switches on near planets and turns off elsewhere. It is a continuous feature of the universe, woven into space-time itself. What changes from place to place is not the presence of gravity, but the strength and balance of its effects. This perspective also explains why gravity feels local despite being universal. In any given place, nearby masses dominate experience. Distant masses contribute quietly, setting background conditions rather than obvious motion. Gravity is always present, but its expression depends on scale. Empty space, then, is not free of gravity. It is where gravity becomes subtle rather than dramatic. Without nearby objects to mark its presence, its influence unfolds slowly, shaping motion and structure over immense distances. What appears empty is still structured. What seems inactive is still governed. Gravity does not need crowded regions to exist. It only needs mass somewhere in the universe to leave its imprint everywhere. Gravity does more than guide motion and shape structure. It also influences time itself. This idea can feel strange because time is usually experienced as something steady and universal, ticking forward at the same rate everywhere. In everyday life, seconds feel identical whether they pass in a city, on a mountain, or deep underground. Yet according to modern physics, time does not flow at a single universal pace. It changes with gravity. This effect is known as gravitational time dilation, a prediction of Albert Einstein's theory of general relativity. The core idea is that gravity and time are linked through the geometry of spacetime. Where gravity is stronger, spacetime is more curved. That curvature affects not only how objects move, but how time passes. In regions of stronger gravity, time runs more slowly. In regions of weaker gravity, time runs more quickly. The difference is not dramatic in most everyday situations, but it is real, measurable, and unavoidable. Two identical clocks placed at different gravitational strengths will not remain synchronized. One will tick slightly faster than the other. Near Earth's surface, gravity is relatively strong compared to higher altitudes. A clock on the ground ticks a little more slowly than a clock aboard a satellite in orbit. The satellite is farther from Earth's mass, experiencing weaker gravity, and so its clock runs faster. The difference is tiny, amounting to fractions of a second over long periods, but it accumulates steadily. This is not a theoretical curiosity. It has been measured directly. Experiments using atomic clocks, which can keep time with extraordinary precision, have demonstrated gravitational time dilation even across small height differences. A clock placed a few meters higher than another will tick slightly faster. The effect is subtle, but modern instruments are sensitive enough to detect it. One of the most important practical demonstrations of gravitational time dilation comes from the Global Positioning System. GPS satellites orbit Earth at high altitude and high speed. Their onboard atomic clocks are affected by two time dilation effects. Because the satellites move quickly, special relativity predicts their clocks should tick more slowly. Because they are farther from Earth and experience weaker gravity, general relativity predicts their clock should tick more quickly. Both effects must be accounted for. The gravitational effect is stronger than the velocity effect, so overall, GPS satellite clocks tick faster than clocks on Earth's surface. Engineers correct for this difference deliberately. If these corrections were not applied, GPS positioning errors would grow rapidly, leading to location errors of kilometers within a single day. The system works precisely because gravitational time dilation is real and well understood. Despite this, gravitational time dilation goes unnoticed in daily life. The reason is scale. The differences in gravitational strength between common locations are small, and the resulting time differences accumulate very slowly. Over a human lifetime, the difference between time experienced at sea level and at the top of a mountain is measurable but modest. No sensation accompanies it. There is no feeling of time slowing or speeding up. This absence of sensation does not mean time behaves uniformly. It means human perception is not equipped to notice such fine differences. Just as gravity feels constant despite small variations, time feels steady because the changes are too subtle to register directly. The effect becomes more dramatic near very massive objects. Close to a neutron star or a black hole, gravitational time dilation becomes extreme. Time near the surface of a neutron star runs significantly more slowly than time far away. Near the edge of a black hole, known as the event horizon, time dilation grows so strong that, from the perspective of a distant observer, time appears to slow almost to a stop. These extreme cases are not part of everyday experience, but they follow from the same principles that govern time near Earth. The difference is one of degree, not kind. Gravity influences time everywhere. Strong gravity makes the effect obvious. Weak gravity makes it subtle. Gravitational time dilation also reinforces the idea that time is not separate from space. Together, they form spacetime, a unified structure shaped by mass and energy. Where spacetime curves more strongly, both motion and time behave differently. This unity explains why gravity affects clocks without any additional mechanism. Time is part of the same structure that gravity shapes. It is important to clarify that this does not mean time flows incorrectly or unpredictably. Time behaves exactly as described by the underlying geometry of spacetime. Clocks do not malfunction in strong gravity. They tick normally according to their local conditions. It is only when clocks in different gravitational environments are compared that differences appear. Each clock measures its own proper time, the time experienced locally. There is no universal master clock ticking in the background of the universe. Time is local, just as gravity is local. What feels simultaneous in one place may not align perfectly with what feels simultaneous elsewhere when gravity differs. This challenges intuitive ideas about time being absolute. In Newtonian physics, time was treated as universal, flowing at the same rate everywhere regardless of conditions. General relativity replaces this with a more flexible picture, where time adapts to the shape of space-time. Gravity reshapes that shape and time follows. Even so, this does not make time chaotic or subjective. The rules governing gravitational time dilation are precise and consistent. They allow predictions that match observation with extraordinary accuracy. Time changes with gravity in predictable ways that can be measured, calculated, and corrected for. The influence of gravity on time also has implications for long-term cosmic history. Over billions of years, regions of the universe with different gravitational environments accumulate different amounts of elapsed time. Clocks near massive clusters tick slightly slower than clocks in emptier regions. The differences are small, but they are real, woven into the universe's timeline. Understanding gravitational time dilation expands the role of gravity beyond structure and motion. Gravity does not merely guide objects along paths or hold systems together. It shapes the rate at which events unfold. It influences how long processes take, how signals propagate, and how histories align. This connection between gravity and time deepens the idea that gravity is not just another force among many. It is a fundamental feature of spacetime itself. Where gravity changes, time responds. Where mass accumulates, the pace of time subtly shifts. For everyday life, this remains an invisible effect. Clocks on a table tick together. Time feels steady. But beneath that calm surface, time is quietly responsive to gravity, stretching and compressing in ways that only precise measurement reveals. Recognizing this does not make time feel unstable. Instead, it places time within a broader context. Time is not detached from the universe's structure. It is shaped by it. Gravity reaches beyond falling objects and orbiting worlds, extending into the rhythm of moments themselves. Gravity reaches its most extreme known expressions around neutron stars and black holes. These objects represent environments where mass is packed so densely that space-time itself is pushed to its limits. The same principles that govern falling apples and orbiting satellites still apply, but their effects are intensified to degrees that strain intuition and demand careful explanation. A neutron star forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. During this collapse, the core is compressed so intensely that protons and electrons merge to form neutrons. The result is an object with a mass greater than that of the Sun squeezed into a sphere only a few tens of kilometers across. This concentration of mass creates an extraordinarily strong gravitational field. Near the surface of a neutron star, gravity is billions of times stronger than it is on Earth. an object dropped from even a small height would strike the surface at a significant fraction of the speed of light. Mountains, if they can be called that, rise only centimeters high before collapsing under their own weight. Matter behaves in unfamiliar ways because gravity dominates every aspect of structure and motion. Escape velocity provides a useful way to describe this intensity. Escape velocity is the speed an object must reach to break free from a gravitational field without further propulsion. On Earth, escape velocity is about 11 kilometers per second. On a neutron star, escape velocity approaches a large fraction of the speed of light. This means that once matter is near the surface, leaving becomes extremely difficult. The immense gravity of neutron stars also produces strong tidal forces. Tidal forces arise because gravity pulls more strongly on the nearer parts of an object than on the farther parts. Near Earth, tidal forces are gentle, responsible for ocean tides. Near a neutron star, these forces are extreme. Objects can be stretched, compressed, or torn apart by the difference in gravitational pull across their length. Spacetime curvature near neutron stars is intense. Paths that would be straight elsewhere become sharply bent. Light itself is affected, curving around the star and altering how it appears to distant observers. Time dilation becomes significant. Clocks near the surface tick much more slowly than clocks far away. These effects are not theoretical curiosities. They're predicted precisely by general relativity and supported by observation. Black holes represent an even more extreme outcome of gravitational collapse. When a collapsing core exceeds a certain mass, no known force can halt the inward pull of gravity. The result is a region of space-time from which nothing can escape once a critical boundary is crossed. This boundary is known as the event horizon. The event horizon is not a physical surface, it is a boundary in space-time. Outside it, escape is possible in principle. Inside it, all possible paths lead inward. The escape velocity at the event horizon equals the speed of light. Since nothing can travel faster than light, escape becomes impossible. It is important to clarify what this means. Gravity at the event horizon is not infinite. Objects crossing it do not encounter an abrupt wall or sudden crushing force, especially for large black holes. What changes is the structure of space-time itself. Directions that once led outward now point inward. Falling inward becomes as inevitable as moving forward in time. Closer to the center of a black hole, space-time curvature grows stronger. Tidal forces increase dramatically. In some cases, these forces would stretch objects into long, thin shapes, in a process sometimes called spaghettification. This effect arises because the gravitational pull at the near end of an object is much stronger than at the far end. Escape velocity and spacetime curvature are closely linked in these environments. As gravity intensifies, spacetime curves more sharply. Motion becomes increasingly constrained. The idea of gravity as a pulling force gives way almost entirely to gravity as geometry. Objects follow paths dictated by spacetime itself. For a long time, neutron stars and black holes were studied only indirectly. Their gravity revealed their presence through effects on nearby matter. Stars orbiting invisible companions, gas heating and emitting radiation as it spiraled inward, precise timing variations in pulsars, which are rapidly rotating neutron stars emitting regular beams of radiation. In recent years, direct observational evidence has transformed understanding. The Laser Interferometer, gravitational wave observatory known as LIGO, detected gravitational waves produced by the merging of black holes and neutron stars. These waves are ripples in spacetime itself, generated by accelerating masses in extreme gravitational fields. Their detection confirmed key predictions of general relativity and provided new insight into gravity at its strongest. Another breakthrough came from the Event Horizon Telescope. a global network of radio observatories that produce the first images of black hole shadows. These images show light bent and captured by intense gravity near the event horizon. They do not show the black hole itself, but the effect of its gravity on surrounding matter and radiation. These observations anchor extreme gravity firmly in reality. Neutron stars and black holes are not theoretical oddities. They are common outcomes of stellar evolution, scattered throughout galaxies, influencing their surroundings through gravity alone. Despite their intensity, these environments do not require new physical laws. The same equations that describe gravity near Earth describe gravity near a black hole. The difference lies in scale. When mass is concentrated enough, familiar effects become dramatic. This contrast highlights gravity's full range. Earlier environments showed gravity as gentle, barely noticeable, or quietly shaping motion over time. Near extreme objects, gravity becomes dominant, overwhelming other influences and revealing aspects of spacetime that remain hidden elsewhere. It is also worth noting that even in these extreme settings, gravity behaves predictably. Paths can be calculated, time dilation can be measured. Tidal forces follow precise relationships. There is no chaos in the laws themselves, only intensity in their consequences. Understanding gravity near neutron stars and black holes completes the spectrum. From barely perceptible pull around small bodies to crushing curvature near collapsed stars, gravity reveals itself as a single interaction expressed across many scales. These extremes do not invalidate the calm familiarity of gravity elsewhere. They contextualize it. The quiet downward pull felt on Earth is one expression of the same phenomenon that bends light, slows time, and traps matter near the most extreme objects in the universe.